All right. I think it's time for me to start. Yep, it is. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just help you, just pray that you be with us today. Help us to glorify you what we do, and just understand again a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. Okay, so let me quickly review a couple things. We defined work, right? Work done by a force F along curve C. That was equal to the integral along C of F dot dr. All right. And I further revealed that the definition of that is the integral, say from T1 to T2. You take your vector field, you evaluate at the parameterization of the curve, and then you take the dot product with the velocity, all right, and integrate that over time. So that's the definition of the work integral. I also told you that if F is equal to minus the gradient of a potential energy function U, and let's say that's over D, all right, so this is some domain. And by that I just mean it's some region of space, all right? Could be two-dimensional, could be three-dimensional, whatever. If you have that F is equal to the minus gradient of U over D, then F is conservative on D. That's important because if it's conservative on D, then we can calculate the work done by such a force using the potential energy function, right? So the theorem that I had was that this, if we take, if F is equal to minus the gradient of the potential energy function, then if I calculate the work done by such a function on a curve, and that curve, let's say, goes from point P1 over here to point P2, all right? So this is my curve. If you calculate the work done by such a function over such a curve, well, then it's really easy because this works out to the integral minus the integral of the gradient of the potential energy dot dr, which by the fundamental theorem of calculus for line integrals is minus U of P2 plus U of P1. So this is very nice because if the vector field is conservative, we don't actually have to go through the rigmarole of calculating the work integral, which can at times be a pain because it's integration, right? We much prefer evaluation to integration. Now, a little bit more context because this requires context. Like, what does that mean? So I told you last time that in 2 dimensions, the gradient of U is partial U, partial X, partial U, partial Y. All right, so that's 2 dimensions. In 3 dimensions, what's it look like? Same thing, but with partial U, partial X, partial U, partial Y, partial U, partial Z. That's 3 dimensions, right? How about 1 dimension, though? I left out 1 dimension last time, and that's actually kind of important. What does the gradient look like in 1 dimension? It's simpler, right? In 1 dimension, you've just got 1 independent variable. So in 1 dimension, the gradient of U is just equal to du dx. So we don't need a vector for 1-dimensional motion, we just have that. So in the context of 1 dimension, if you have F is equal to minus du dx, this is conservative force in 1D. All right? So another way to say this is this gradient that I introduced last time. It's just the 2 or 3-dimensional analog of the derivative. And we need that in physics because physics isn't just 1-dimensional. It's also 2 or 3 dimensional. Now some of you might balk at this because it doesn't look like your high school physics course. That's right, this is not high school physics, this is university physics, and as such we will use calculus 3 at times. So, but I also try to, provide you an on-ramp in here, which is why some of your homework hopefully helps you explore these ideas. But I think, to be fair, I should work out an example, right? Which actually makes use of the, the full definition on an interesting example. Well, I'm not sure how interesting it is, but possibly interesting example. Before I go further, any questions? What did we prove last time? Last time we proved that if the net force is conservative, then what? Then energy is conserved, right? If net force is conservative, then the sum of the kinetic plus the potential energy is conserved. That's true in 1, 2, or 3 dimensions. So example 1 here, we try to actually give you a little bit of a calculation here. Let's look at something that's kind of an interesting curve, something like this. It's not a very good picture of it, but here's a curve in 3 dimensions. The parameterization of it is this. T squared, T cubed. And if you don't mind, I'm going to suppress the alpha, beta kind of stuff. All right, let's just assume that we're working in units of meters and seconds and so forth, if that's okay with you guys. You're like, if you could do that on the test too, I'd appreciate that, right? So, I feel guilty sometimes if I put a problem on the test where I don't have units. It feels wrong. Anyway, so there's the curve. That's called the twisted cubic. It kind of spirals up and it keeps getting more and more out there and going up faster and faster because as you get past 1, the third component grows faster and faster, right? Okay, so let's calculate the work done. Let's look at a vector field. And let's let the force be equal to, I don't know, let's say x plus y, x hat, plus y squared, j hat, plus, let's say x, j hat, listen to this, y hat, right? Plus x, z hat. In the other notation, what would this look like? So if we use the bracket notation instead of the vector hat notation, this would look like x plus y, right? Y squared and x. So this is a kind of weird force, right? It's different in different places. It's a genuinely interesting force field. All right. What's the work done by this force field on a particle that traverses this twisted cubic? And to keep the math easy, let's make this go from 0 less than or equal to t less than or equal to 1. All right. So basically, we're just looking at the part of this that goes up a little bit. I don't know. It's probably just basically like this piece here. I'm not sure exactly. It doesn't really matter exactly what it looks like. We can still find the work done. Okay, so let's calculate the work done. How do we do it? We need to calculate, let me, instead of just writing the integral down, let me assemble it bit by bit, okay? So what do we need to calculate the work? We need to calculate, well, dr dt is one thing we need. Let's get that out of the way. What's the velocity here? So the velocity here, dr dt, is just what? Differentiate, right? 1, 2t, and 3t squared, yeah? So there you go, that's the velocity. Now, the other ingredient I need is I need to evaluate the vector field at the parameterization, right? At the r of t. In other words, I need to look at f of t, t squared, t cubed. What I mean by that is I need to put x equals to t, I need to put y equals to t squared, I need to put z equals to t cubed in the formula for x. So the way that works out in this case, right, so x is equal to t, so I put t, y is equal to t squared, so I put plus t squared, all right? What's y squared? Well, y squared would be t squared squared. And then x, well, that's easier. X is what? Just t. So there you go. All right. And then what we're going to integrate is f of r of t dot product with the velocity dr dt. And this quantity deserves a separate discussion anyway. So I'm building my way to do the integration. I just don't write, I mean, you could just write down the integral and just do it, but I think it's more fun to assemble it in pieces like this. So t plus t squared squared is t to the fourth. You got t, and you're taking the dot product with what? 1, 2t, 3t squared. So what's this work out to? We have t plus t squared times 1 plus t to the fourth times 2t plus t times 3t squared. This is the dot product. X times x plus y times y plus z times z. You all need to know this going forward. Some of you are pretty shaky on this on test 1. It's not a good place to be. But you know that. Anyway, there's still hope. You just need to fix things before the next test. Let's see here. T plus what? I got a t squared. Yeah. And then what? Looks like a t to the fifth. I'll count this one next, though. Plus 3t cubed, yeah? Plus 2t to the fifth. All right, there we go. Does anyone know, can anyone tell me what this represents physically? This actually has a meaning, what we're about, what I've just calculated. What is this that I've calculated? Yeah?
Sort of like the force in the direction of the motion.
This is the force in the direction of the motion. That's kind of it. But it's not a force, right? Because it's a force dot. This is F dot V, right? How about that? If I say it that way, does anybody remember from your high school physics what F dot V was? No, it's not momentum. Think about this. This is the thing we're integrating, right? We're adding this up to calculate the work done, right? So essentially what this is the work per unit time. What's this called? Power, right. This is the power developed by this force along the curve at time t. That's what this is. This is the power developed by F at r of t. And so to calculate the work done, you integrate the power. That's another way of looking at the definition. So now we need to integrate that to calculate the work done. Integral of, well, all of this, right? So integrate from 0 to 1 of t. This is my favorite kind of integral. I don't know about you guys, but this is absolutely my favorite polynomial integral. We integrate from t to 1. This one's really, really easy. So what you got a half plus a third plus 3/4 plus 2/6. Is this in the way? I still got some more cord. Yeah. It was for a good cause. It survived again, but you know. Where was I? Can you see better now? I was going for something. What was it? Oh yes, calculator. But you guys probably can already tell me what that is. What does that work out to? I shouldn't really need a calculator for this, should I? Oh, fine. I don't want to think. So what I get is 23 over 12, which would be a really annoying answer to give in here. So let us give it proper. Let's say 1.917 approximately, okay? Now, if we're actually working, yeah, in units of meters and seconds and kilograms, what would the units that I should be putting on this are? What are the units of energy? We haven't really talked about that yet, have we? So this should probably have units of joules, right? A joule is a Newton times a meter, which I'll talk more about here in the next example. J is for joule. So any questions? Right. Let's see here. So this force we're working on here, what was the starting point and the ending point of the curve? The starting point was r of 0, right? What's that? It's 0, 0, 0, right? That's the starting point. Where's the ending point? Yeah, 1, 1, 1. Right? So this is end. And obviously that's an interesting curve, right? What if we calculated the work done by this force field along the line that goes directly from 0, 0, 0 to 1, 1, 1? How would you do that? So I just gave us the path, right? For this example. Example 2. Let me put this silly thing away. Oh, yowzers. Yow. Sorry, guys. So same force, but let's calculate the work done by the path that goes directly from 0, 0, 0 to 1, 1, 1. So what would the parameterization be in that case? R of t would be what? You do, if we follow the thing I did last class, we do the initial point plus t times the difference of the points, right? Of course, so I'm just going back to the trick I introduced last class. You know, you take the initial point plus t times the final point minus the initial point. That gives you the parameterization of the line. This is a general trick. But in this case, it just works out to what? It's really simple. T. So that's the parameterization of the line that goes straight from 0, 0, 0 to 1, 1, 1. And we can calculate the work done along that path by this force field, right? So what's dr dt? A little bit easier, just 1, 1, 1. And what's f of r of t in this case? It's f of t. And we plug, it's very easy to think about. Everything is t, right? So you just plug in t into the x, into the y, into the x here, right? So you get 2t, t squared, t. That's it. Then we can calculate the power done along this curve. What's the power for this one? It's going to be different, isn't it? So we've got apparently 2t, t squared. It is so hot in here today. Ay, ay, ay. I'm not enjoying this. I mean, I'm enjoying the physics, but temperature, not so much. So what do you got? You just got 2t plus t squared plus t, also known as 3t plus t squared. Then to calculate the work done, what do we get? We have to integrate the power. In this case, it's 3t plus t squared. Again, from 0 to 1, because that's how we set this up. That's the whole trick I introduced last time to parameterize the line, going from time 0 to time 1. What's that work out to? I think we get 3/2 plus 1/3 which is what? 1.5 plus 0.333, so 1.8333333, yeah? Hold on a second. Compare this example 1 work and example 2 work. All right? What do you see about them? Can you tell me something about these two examples? Same force, right? Same starting and ending points. Agree? Both curves start at the origin and go to the point 111. But what's the difference?
Paths.
Yeah, they're different paths, and they gave you what? Different work, right? So this is an example of what's called a path-dependent force. This force has a path dependence. So if you have initial point and final point like that, and you have one curve, let's say C1, and another curve C2, like this, and if you have the integral over C1 of f dot dr is not equal to the integral over C2 of f dot dr, then f is not path independent. So it turns out that the interesting thing is when your force is path independent. This one is not path independent because in fact it's path dependent. Yeah.
On this board, where did you get like the 4th line from? Did that come from the 3rd line on the other board? Or?
Oh yes, same force. Same force. I should say that. I should write that. My bad. So same force field. And so, and specifically to answer your question, over here we had x plus y, y squared and x. So I'm just setting x and y and z all equal to t.
Yeah.
Of course there's no z here, so that's kind of boring, but yeah. Other questions? Yeah.
When you get an answer for the integration, is it okay to leave that as a fraction or do you use it for the
I prefer to have decimals in here just because, you know, it's physics. I try to leave answers in decimals. I do sometimes, my math is showing and I'll leave things as an exact fraction or a square root or something, but we do generally try to put things in decimals in here. If you left it as an exact fraction, am I going to take points off? No, certainly not. Almost certainly not. I have bigger fish to fry, you know. Now, if you leave units off of it, and it's supposed to have units, then I'll get you. Like a lot of you lost a point because you didn't write Newton on, what was it? 3. There was one, I can't remember. I took off, like half of you lost a point for not writing Newton. So now you'll remember. Now this one here, I'm working without units, right? So this is, in some sense, bad physics, right? To be more obnoxious, I should really put in like dimensional multipliers here to make it have explicit units of meters and explicit units of newtons and stuff, but I'm leaving those off at the moment just to decrease your cognitive load for following these two examples. So my question to you is, can this force be conservative? Think about this. If the force is conservative, look back over here. See this right here? Think about the point 1. Think about the point 2. Right? You got two curves. One this way, one that way. They both have the same terminal points, starting and ending points, right? If the force is conservative, what's the value of the work done? See, it doesn't matter if you use curve 1 or curve 2 because the value of the work done just depends on the difference in the potential energy function before and after. So what that means, right? What that means is the force that we looked at in example 1 is not a conservative force. It cannot be because we calculated the work done over two different paths and we found different answers, right? Again, with the same starting and ending points. Now, follow-up question. This is a little bit trickier. What if the work done in example 1 and 2 had been equal? Would that have allowed us to conclude it's a conservative force? No, you have to have it for all possible paths for this to work. So the existence of a pair of paths where it matches wouldn't force it to be conservative. It's evidence in its favor. The ultimate judge of whether or not it's conservative or not is, can you write the force as the negative gradient of a potential energy function? All right? So that's that. So if you actually tried to solve like partial u partial x equals to minus x minus y, and you tried to solve partial u partial x, partial y rather, equals to minus y squared, and if you tried to solve partial u partial z equals to minus x, you could try to solve these, right? And what would happen is you'd get a contradiction. You would arrive at a contradiction in the process of trying to solve for u. You can't do it. Let's look at one where we can, okay? Because actually, it's pretty easy to find the potential energy function from a given force field. I think I did one of these last time. I'll do one more and then we'll go on with our life here. But example 3, let's let F equal to, let's say, x squared plus xy squared, comma, y squared plus x squared y. And then I'll say, to make it interesting, let's find the work done on curve from, let's say, 1, 2 to 3, 4. Let's do this example. How would you do it? So first of all, if anybody comes up to you and says, find the work done on a curve that goes from one point to another, and they don't tell you what curve it is, that's a dead giveaway. The only way for that question to make sense is if the force you're dealing with is conservative. Otherwise, what curve are we talking about, right? Because there should be a path dependence in general. So for this problem, for this question to even make sense, that had better be a conservative vector field, right? So let's think about it. You want partial u partial x equals to minus x squared minus xy squared, and you want partial u partial y equals to minus y squared minus x squared y. Now, we tend to teach students like a rigorous way of doing this, but there are non-rigorous ways of doing this, which are basically just guessing. And I would encourage you to guess and check, right? Guess and check is the way to go in here. Basically, what you want to do is you want to do an integration with respect to x, and you want to do an integration with respect to y. Then you want to compare those and write down the answer. That's the method. So let me refer to that as sort of, it's kind of this kind of thing, and it's kind of this sort of thing. In the sense, I mean, you integrate holding y as a constant, or you integrate holding x as a constant. What would the integral of this be? X squared integrates to x cubed, right? Divided by 3. So that suggests a minus 1/3 x cubed, right? How about this? When you integrate that with respect to x, what would it be? Yeah, minus 1/2 x squared y squared. Very good. And then here's the thing that's a little bit tricky. You get a constant, right? But what is a constant here? Well, to be fussy, the constant could actually be a whole function of y, right? So traditionally, people will write something like c1 of y here, just to fess up that the constant here, in fact, could be a function of y. All right? What if we do the other integral? What do we get? Integrate minus y squared, what happens? Minus 1/3 y cubed, right? And how about this term?
Minus 1/2 x squared y squared.
Minus 1/2 x squared y squared, that's right. And then we have to confess that plus a constant C2, possibly of x, right? So what's my potential energy function then? I mean, think, all right? So, well, I'm going to do the easy part. Obviously, this is part of it, right? Do you need two of them? You don't need two of them. You only need one, right? One of those will do. And then I do minus 1/3 x cubed minus 1/3 y cubed plus 42. I'm just messing with you. You don't have to add 42 there. You could add 10, you could add 3, you could add whatever number you like. The potential energy is not uniquely given, right? The potential energy has a choice. There's a choice of reference. You can adjust this constant to be whatever you want. We'll put it back to 0 just to be less weird, okay? There we go. Get rid of that. There you go. You can calculate now. Check it. If you don't believe me, try it out. In fact, f is minus the gradient of u now, right? It will work out to, as we said, x squared plus xy squared and y squared plus x squared y. You can try it out to calculate the partial derivative with respect to x. Will take you to the first component. The partial derivative with respect to y will take you to the second component after you multiply by minus 1. Do you see it? When I partial differentiate this with respect to x, that term drops out. This piece gives me 2xy squared. The 2 cancels with a half, leaves me a minus xy squared. Right? Minus a minus xy squared gives me that term. Then this 1/3 x cubed, when I differentiate it with respect, gives me x squared. Minus a minus x squared gives me that term. So it works. Okay, so anyway, what's the work done? So all we got to do is calculate, how's it go here? Minus u of P2 minus u of P1. What were P1 and P2 in this context here? So P2 was 3, 4, yeah? I mean, so this is plus this one. Plus u of 1, 2. And then all you got to do is just plug the points into the potential energy function and see where that takes you. If you don't mind, I'm going to do the 1, 2 first. So that gives me like minus 1/2 of 1 squared times 2 squared